Bentar lagi pulang ya? Ini mau ada pun.
Yes, ladies and gentlemen, we shall begin in 2 minutes. So, for those who are still outside, can you please come to the auditorium? Okay, it's 1 o'clock, so we shall begin. Good morning, everybody. Assalamualaikum warahmatullahi wabarakatuh. So, today is our second day in the Indonesia-APCTP workshop on quantum computing and simulation. Today we have 4 speakers. There will be 2 speakers in the morning and 2 speakers in the afternoon. In the morning, we will have Dr. Aziz and Dr. Gagus Sunnardianto. Dr. Aziz will be speaking first. We will also have a group photo in the lunch break. And of course, you can find all the details in the website. And I shall introduce our speaker for the morning, Dr. Majidi. He is a faculty member at the Physics University of Indonesia, where he is a member of the Undergraduate Physics Group. Dr. Aziz graduated from University of Indonesia for his undergraduate from University of Cincinnati, 2006 under the supervision of Dr. Mark. His dissertation was computational studies of ferromagnetism and strongly correlated electronic systems. His research focused on modeling of strongly correlated systems such as magnetics, qubits, and dilute magnetic semiconductors to predict their thermodynamic, transport, and optical properties. In most of his research, he employs the method of dynamical field theory and its extension, as well as simpler yet rich of insight methods like type union approximation. He has also developed algorithmic implementation of magnetic-based techniques such as the GW and other diagram approximation to study effects of electron and electron interaction revealed in optical responses of strongly correlated systems. And he recently started activities in using quantum computing technique to solve problems in quantum physics. Aziz, the time is yours.
Thank you very much, Dr. Hayok, for the introduction. Good morning, everybody. First of all, I'd like to thank the organizer for the opportunity to share my knowledge this morning. Probably I have to say some disclaimer that my talk is probably not quite related to quantum computing in the sense that I'm not going to be talking about the details of how we do quantum computing, but at least I want to share with you about some problems that may potentially be worthy of solving it using quantum computing. So I put the title Constructing Realistic Type Binding Hamiltonians. So this is the outline of my talk. So the first one, I just want to show you at least a particular problem in mathematics or in algebra in general about solving eigenvalue problem that we traditionally, if we don't have the intention to take advantage of the quantum algorithm, we usually use just direct diagonalization. So we solve the secular equation, and after finding the eigenvalues, then we try to search for the eigenfunctions or eigenvectors corresponding to the already obtained eigenvalues. So that is probably just to show you the motivation of what I later on explain more on the technicality. So next, I want to share you why and the reason for why we need to do realistic modeling of electronic systems in solid systems. Then I want to briefly review the concept of type binding model using atomic orbitals. I will address the problem of the presence of overlaps between neighboring atomic orbitals. Then I move on to introduce to you Boolean functions as a means of mimicking atomic orbitals that suppressing overlaps between neighboring functions. Single orbital type binding model using Boolean functions. And then the generalization into multi-orbital type binding model using Boolean functions. Type binding model in second context formalism. And two last items are about how to use existing softwares to help us obtain the type binding parameters which we can eventually use to construct our realistic modeling, and some example of how we finally come up with the results of calculation of the instruction. Okay, so let me start with the motivation. So in physics, especially in the condensed matter area, physics, we often need to deal with solving Schrodinger equation, either time dependent or time independent. So what I'm trying to talk about more today is about the time independent Schrodinger equation. So essentially, if it is not necessarily about solving Schrodinger equations, I'm mainly talking about the eigenvalue problem, meaning we have some operator, or we may have the operator in the form of a matrix, for instance. Then how we solve to diagonalize the matrix to obtain the eigenvalues and the eigenvectors. So that's essentially the problem I'm trying to introduce to you, that we probably can alternatively solve it using quantum computing rather than potential method using classical computing. So in trying to solve the problem, the typical method that I think most people may use is the direct diagonalization, meaning we compute the determinant of the matrix of the Hamiltonian minus the eigenvalue multiplied by this is identity matrix, right? So after finding the eigenvalues, later on, we probably need to find the eigenvectors or the eigenfunctions corresponding to each of the eigenvalues. So this is a typical problem we usually do using cluster computing. But doing it with quantum computer, in order for us to be able to take advantage of the superiority of quantum computer, is that the idea is that we want to make the process of computing our problem by utilizing the quantum states, meaning that if we let the form of our problem remain as usual, like this, then we have less opportunity to utilize the quantum states. So, but if we form the problem into calculating the expectation value, it's basically equivalent to obtaining the eigenvalues of the Hamiltonian, provided that we know the quantum states that we use to compute the expectation value. Of course, when we have the problem in hand, we don't know yet the answer, right? Meaning we don't know the eigenstates of the Hamiltonian. So if we do this calculation, it is only meaningful to say that we have the results only if we already know the quantum states, I mean this side, yeah, right? But at least, although we don't know yet the correct quantum states that will give us the correct results of the values, we can do or we can search the correct eigenstates by doing variational method. I think this is the relevance of my talk because it is going to be continued by the next talk by Dr. Gagus. He's going to talk about variational, something related to variational method in quantum algorithm. So that is the relevance. So I actually I'm not gonna really talk technically about how we do this. So I'm just giving you the motivation. So the rest of my talk will be basically how to come up with the good Hamiltonian reflecting realistic problem. So that's basically what my talk is about. So let me tell you about the need for realistic modeling of electronic systems in solid-state crystals. So physical phenomena and properties of materials generally depend on the details of how electrons are situated in the system. Meaning that the crystal structure of the material that provides the potential energy to the electrons and the interactions among the electrons, as well as between the electrons and other entities, such as defects, impurities, or other quasi-particles, those can affect the results of our calculations. But since the problem, if we really want to come up with the exact answers, the problems may be complicated enough for us to get the correct answers. In that case, then we may need to consider several possible situations. Typically, there are three situations that we may face. First, if the effect of the crystal structure is considered more important than the interactions. Second is if the effect of the interactions is considered more important than the crystal structure. So typically we deal with two terms of the Hamiltonians. The first one is the non-Ketut part, which contains the detailed information about the problem upon neglecting the interactions, plus the interaction which plays the role as the relation server. So we need to compare, we need to consider which parts are actually very crucial to handle. So the third one, if both the crystal structure and the interactions are comparably important to some degree. So taking a full account of both effects of crystal structure and interactions is usually a difficult task or computationally very expensive. So alternatively, we may do some strategy to handle the situation. So here, I'm supposing that we are in the third situation. So we want to handle the problem corresponding to the third situation by taking a partial account of the effect of the structure in the form of type binding based modeling. So as of today, I think all conventional physicists agree that if we want to solve problems especially solid crystals, density function theory as the initial approach is the most powerful and considered best to get the solutions. But unfortunately, KFT may not do a good enough job when there is existence, when there exists some strong interactions that may lead to certain exotic properties of the materials that cannot be handled without really taking into account the effect of the interactions. So in that way, we want to handle the interactions, but we don't want to be so much burdened by having to handle the details of the non-interacting part of the Hamiltonian. So what we wish to do is to come up with some effective non-interacting part of the Hamiltonian. So in the sense that if we compare between the results of DFT, for instance, that can provide us with all the bands in the band structure that we need, right? So if not all the bands are actually important, then we may simply need to select some of the bands around the band level. So for that purpose, we may like to do DFT calculation, but not for the purpose of using DFT calculations alone to solve all problems. Instead, the DFT is only used to help us obtain the parameters for our modeling. Then, with the type binding based modeling that we construct, later on we may like to add the interaction terms by some way, and we may choose, depending on how rigorous the results we want to achieve, we may choose a certain level of approximations. So here's the illustration of how the time binding model works. So consider, for instance, if we have an array of atoms. Let me simplify the problem by imagining that we have just one-dimensional world consisting of an array of atoms, where each atom has an atomic orbital. So this is just an illustration, my illustration about how the atomic orbital forms. Don't worry about, don't like with this shape, we can simply replace it with just a zero component, so it doesn't matter. So what matters is that as wave function extends to some distance that allows overlaps between neighboring actors. Okay. So this is the illustration. So this is the typical original Hamiltonian that we have in the crystals, where assuming that we can reduce the n particle problem to the single particle problem by at least initially we assume that the particles are non-interacting, so that we can simply represent the whole problem by solving as a single particle Hamiltonian like this, when the second term is the potential experienced by one electron due to all the effects from one atom existing in the material. So we know that in crystal we have periodic situation that makes our wave function is subject to translational invariance. Right? So having this translational invariance property, there is a theorem by Bloch. The Bloch theorem says that the form of the wave function has to be of this form, where there is part of the function that follows periodicity of the crystal like this. So if we solve the Hamiltonians and if we succeed to obtain the Bloch functions, the Bloch functions will carry usually two indices, where n is the index of Z. So n is that index. Where this value index comes due to the fact that in our periodic system, in the A space, we have what we call reciprocal translational electric spectrum G. So G has this index n, and this index n is actually what makes us finally have index. So okay, so as we want to proceed to construct a time binding model, imagine that we want to express the Bloch function on the left here. So we want to express the Bloch function as a superposition of atomic wave function. So I represent this I m as atomic wave function, where in this case m is the index that is associated with the orbital. Okay? But as I told you earlier, n is the index that corresponds to band. So this is the band index, this is orbital index. So these two indices are two different things, but they span the same basically the same Hilbert space, meaning that if they form like a set of n indices, capital N indices for m, then the same way it does for the index n, meaning that if we start with the model with, let's say, 10 orbitals in our unit cell, then we should come up with 10 bands. So that's what makes the two indices related. So but they are different, meaning that if we say that we have index m in here, then we cannot directly associate m with m again over here. So which means that there should be some transformation that brings from the set of orbital indices to the set of n indices by this unitary transformation. So this is some unitary transformation. Now, to do further simplification, let me introduce single band or single. So sometimes when we number of band is almost the same as the number of start with. So the complicated expression that we have above can now be simplified into this more simple expression where now we can get rid of this n as well as m indices and the unitary matrix here. So this is the expression of the law function expressed in terms of atomic orbitals. Okay, so if you want to try to solve so assuming that we already made a guess of the law functions simply by constructing from the atomic orbitals. So basically we don't do any calculation. We only assume that our atomic orbitals are good enough for us to construct our law function, which is just an assumption that this we classified simply by the results whether they are good or not. So if supposing that the law functions that we obtain by using atomic orbitals are good enough for us to do this calculation, the expectation value, right? Then after some algebra, we can come up with the eigenvalues with index k, meaning for every k point in the reciprocal space, we can have the energy that forms the dispersion relation of that model. Okay. So apart from the detail, what I really need to emphasize here is that according to this formula, the calculation of the values demands that we know the overlap. We know the value of the overlap between orbitals. So because of that, then without knowing the values of the overlaps of the orbitals, of course, then we cannot really obtain the values of the values. So this is a problem because besides that it gives us some extra work to do if we want to calculate or to come up with the correct eigenvalues. The formulation itself is somehow not so nice because we cannot simply connect the energy in the space with the this is what we call Hamiltonian matrix in the real space representation. So besides that, we essentially don't want to do calculation for the overlaps. We also want to have a much nicer eigenvalue and the real space representation. So again, consider this formula. Supposing for whatever reason we just want to make that case, right? Just to that's going to be the overlaps. Then, taking this to be zero, it turns out that we got a very simple relation between E sub k and the H I j, that is the Hamiltonian matrix. So, and that really gives us a relation that we can claim to be just Fourier transformation, right? So we obtain the Fourier transformation relation only if the overlaps between the atomic orbitals are taken to be zero. What does this actually mean? Well, it actually means that initially or previously we didn't say that our basis, the atomic orbitals that we are taking as the basis sets, to have orthogonal properties. So they are not orthogonal by the fact that exists the overlap, right? For the functions, for two functions to be say orthogonal, they have to have no overlap, and their overlap should be zero. Okay? So meaning that if you really want to use the formulation that where the orbitals that we use have all orthogonal properties, and we have the simple relation in the form of full transformation, then we have to find some way of getting rid of this overlap. Right? Okay. How do we do that? So well, long back the development of solid state physics, Woodian introduced the so-called Woodian functions. So Woodian functions are functions that are obtained from the presumably or incorrect block functions by doing essentially Fourier transformation this way. So this process actually makes the block function is extended to become localized function centered at every atom. Okay. So is this the same as the atomic orbital? Of course not, because atomic orbitals are the functions obtained by solving atomic problem, and I turn around atomic nucleus, right? Whereas Wally functions are functions that are obtained after we have block functions, then we do Fourier transformation. So they are not the same. But somehow we want to use Wally functions to act like atomic orbitals, so that we can reconstruct our purpose of doing angular modeling, but using basis sets that can get rid of the overlaps, so that the basis become orthogonal. So this is the property that we demand from the Wally functions. We use the orthogonality property. Okay, so if we have assuming that now rather than using atomic orbitals, we use Wally functions, then definitely we can construct our Hamiltonian matrix in the real space representation and come up with simple Fourier transformation relation to get the events, right? Event structure. So now our Hamiltonian matrix in real space representation has to be constructed not by atomic orbitals, but rather by Wally functions. Okay. Okay. Now let me generalize this idea, because what we want to be able to solve is not the simple hypothetical problem of just a one-dimensional world of atomic arrays, but we want to go back to the actual system, which is crystal, three-dimensional crystal, right? So in that case, then we need to generalize the formulation by taking into account the fact that we probably in a unit cell, we probably don't have only one atom. We may have more than one atom. We may have many atoms, and not just many atoms, but in one atom there may be many orbitals, right? So meaning that if we take a unit cell in our crystal, there may be many orbitals that we have to take into account. Right? The problem is we really need to take all the orbitals taken into our constructive model. Of course, our initial motivation is not to do so, because otherwise then let's just go back to the DFT. The DFT already handled all the banks, right? Already give us the results, the structures from all the banks. Okay? Of course, we want to only select some orbitals that are most relevant for our problem. So, okay, before going into that, let me at least explain the illustration for generalizing single band type binding model into multi-orbital one. Let's suppose that each of these parallelogram is a unit cell where, let's suppose that it only contains two atoms, where in each atom, here, the atom A has two orbitals, atom B has three orbitals. Of course, the 2 and 3 orbitals are assumed to be the self-ones. Okay? So then, including the spins, the spin and the orbital, overall, our Hilbert space is formed by 2 plus t, 2 plus 3 times 5, then multiplied by 2, so 10 by 10 by 2. So our Hamiltonian matrix will have the size of 10 by 10. Okay. Okay. By having more than one orbital in our unit cell, then we have to go back to the formulation that I showed earlier, right? Where we need to be able to deal with this unitary transformation. So our block function needs to have the index, and the only function also has to have the orbital index, like this. Okay? So this relation should be consistent with the definition of Woolley function as we had before. So these two equations are actually not inverse to each other, but the second one is just a requirement for the two functions to be consistent. Okay? So here the unitary matrix is U and N of K need to be found to make the Woolley function maximally localized. Why do we need to make the Woolley function maximally localized? It is because we want the Woolley function to have as small as possible tail, so that we can get perfectly zero overlap. So that's the ideal case that we want. Okay? Of course, if we cannot achieve the ideal case, at least we expect that the overlap can be made as big as possible. Okay, then that way we can define our Hamiltonian matrix in the real space representation given by this relation. So these H, I, J, and M are what we commonly refer to as the type binding parameters. So when the index M and N are equal and I and J are equal, then the element has a special name called the on-site energy. So the among the matrix elements, there is a special element, actually special term in the diagonal element that is called the on-site energy. On-site energy means the energy associated with every orbital after being collected. Usually, it is equal to the original atomic energy corresponding to that orbital and collected by the effect of the presence of the other atoms. Okay, whereas the other elements are then called either hopping parameters or hybridization parameters. We usually say hopping to represent the parameter connecting two volume function between two atoms. So the hopping is like a hop of a frog, like from one point to another point. So whereas if we really want to represent the parameter associated with two different orbitals but still within the same atom, we call it hybridization parameter. But if you don't care about the name, they are basically just matrix elements. So if we only want to care about them as matrix elements, we don't even need to manipulate which one we have to call one side, which one we have to call copy parameters and hybridization parameters. Okay. Let me show you now how we show that the second one, the type model can be expressed in the second quantized formalism. So normally, in computer theory, we express the Hamiltonian in terms of field operators like this, whereas the term the sandwich between the two field operators is the Hamiltonian, basically the Hamiltonian that I showed you already earlier. And here I put another subscript 0 just to mean that this is the non-interactive form, because doing this formalism, usually you have the goal of solving the whole problem, including the interaction theory, by implementing the computer theory techniques, basically. So, by the atomic potential that I put in here, I can certainly say that it may include also spin orbit coupling. I mean, if we want to not neglect spin orbit coupling, it basically can be absorbed into this expression. So, I mean, this formalism can hold generally used for system with spin orbit coupling. Okay. Next, we need to express the field operators in terms of creation and annihilation operators. So we do it this way, where this is the spin-off, the spin function of electrons. So doing this transformation, as we then substitute these two expressions of field operators, family field operators, then some algebra, we can get this expression. So now the Hamiltonian is expressed in terms of creation and distribution. So if we see that the Hamiltonian simply has this form, that means this should be an exactly solvable Hamiltonian, because the Hamiltonian only contains product of k negative and k. So every time we see a Hamiltonian expressed as some number or some coefficients multiplied by creation and isolators like this. This is just an example solvable problem. So the way we solve the problem is so basically, if we see the expression of this Hamiltonian, we are only saying that we haven't seen the values in this expression because the indices of the creation and annihilations are not the same. So supposing that we have the two indices belonging to the k negative and k are just exactly the same, that means we have diagonalized the Hamiltonian. So if the Hamiltonian is already diagonalized, then whatever is sitting in here tells us k index. Basically, as simple as that. Of course, we cannot simply change the non-diagonal expression into the diagonal expression. What we have to do is either take a use of transformation. So what I want to say is that this is the ingredients that we need to have if we want to construct diagonal equations. Okay. Further, if we do full transformation like this, then we should be able to finally come up with the Hamiltonian that has already same indices for the first index. Although we may still have different indices for the second one, which means that we still have a matrix. We still have a matrix that is non-diagonal, but at least we already have one, just a single k index rather than ij, like when we have it in the real space representation, we have I and j two different indices. That means the Hamiltonian was not diagonal in real space, but now it has become diagonal in real space. So, but of course, after having these results, the next step, the next final step that we do is just diagonalizing this. So, what I want to show you next is basically how we obtain this matrix by the help of the continue. So, those who are not yet familiar with PFD are probably can have some reading. So, this is just a brief overview about the PFD. So, so basically, what I want to show you is there is a simple procedure that we can do using the software. In this case, if we use quantum espresso, for instance, free package to solve the PFD. We can use quantum espresso to obtain essentially the wave functions and the list of the system. But our purpose for using the PFD results is not just to go on with the PFD results, but rather we want to make a selection. For instance, This is the original DFT results for the structure of gallium arsenide already taken into account so just take this as a knowledge that we agree this is typically the result, right? But we don't want to use all the bands to make further calculation. So what we want is just to select several bands around the timing energy, then we go on with further calculation by taking into account the interaction term. Okay. So so the procedure is by by using another software. This is body 90 to construct the body functions. To give us the parameters, high parameters, and to allow us also to select only a few bands. So let me skip the details. So basically, this is the illustration of how we, from the original results of DFT, all this complicated structure, we only want to select some of the bands. For instance, since this is the time energy, then we want to only include a few bands around the time energy. Of course, the farther away certain band relative to the location of the time energy, that less and less important. So we only take into account the close one to the time energy. So there is some procedure for doing so within monitoring. So finally, so what I want to show you is that so we can finally obtain only a few bands, but these few bands, if our calculation is very good, then basically we still can reproduce exactly all the exact temperatures of the bands that we will include in our model, high-five model. So our high-five model has been guaranteed now to produce the non-interactive results that still remain in the result, but we can only get rid of the other bands. As we only want to see the dynamics of these once interactions. So that's basically the motivation of my talk. Sorry. Yeah, thank you for your attention.
Thank you, Dr. Aziz. Now, is there any questions from the audience?
Thank you very much, Dr. Aziz, for your presentation. In my experience, when solving second quantized Hamiltonian, when using quantum computing, I transform the equation and animation operator using a previous method, like the generator and other method. Why in this calculation we don't need to transform the equation and animation operator using that method? Thank you very much.
So as I mentioned in the early part of my talk, so what I talk in details is not how to do the quantum computing part. So I'm just showing you some example of problems in connection basic that may be worthy of solving it with quantum computing. So that so I essentially only show you how we form the matrix. Then after having the matrix, then we have the Hamiltonian, right? Then after having the Hamiltonian, it's up to you how you want to solve it. So if you really want to solve it the way you usually do it,
Thank you.
Thank you, Professor. I have a question that if we want to calculate using type binding, and then let's say we have graphene, and graphene itself constructed by carbon atoms, which has one s orbital and three p orbital. But when we calculate the graphene, we have to know that the orbital is not s and 3p, but sp2 and 1 pz orbital. My question is, how can we just calculate type binding without knowing the hybridization? Because, in my experience, we have to know first the hybridization and then try to calculate and construct the Hamiltonian using the specific hybridization. So, for example, if we calculate graphene just using S and PP, PXP, YPZ, so we couldn't find the safe band structure obtained by DFT. So, my question: how to calculate that binding without knowing DFT band structure?
I think it is exactly the purpose of my presentation to show you that we have to do some pre-calculations using DFT to obtain realistic parameters to construct our type binding model. I mean, without doing DFT, of course, the type binding model itself is independent of whatever parameters we want to put in our model, right? But now the question is whether our model will become realistic or not. For instance, if we really want to produce the linearity, the graph form, for instance, just to obtain a linear dependent specialization for the graphene, definitely we cannot construct our Hamiltonian with something with off-diagonal Hamiltonians with dependence sitting on the off-diagonal, right? And we can simply choose whatever the values, the value corresponding to our Bernoulli velocity, right? Which probably by the knowledge of in terms of other people's research, for instance, then we may know we simply use the and that way we can produce our type binding structure maybe already good enough up to showing the right? But if you want to know more than that, since we, for instance, if you want to do not just transport calculation, but also optical. For optical calculation, we probably need to go a bit further, TEV, above, below the level, right? In that case, then we really want to have correct structure, not just the linear part, but also the blocking and all the details. And in that case, if we have some knowledge that we may probably use without really having to go to the AP, any means of getting realistic parameters may do, right? When we construct the, okay, if we really want to do more realistic type of calculation without really using DFT, at least what we have to do is go back to the real space representation, then try to tune the parameter value so that we can at least compare with any existing experimental results so that our choice of parameters become reasonable. So that is another approach of doing type binding calculation without having to go to DFT. Of course, the choice of going to DFT The answer to that question is I should refer to the guideline for using more than 90 days. So in there we can the procedure. There are also some warnings of doing it carefully because if you don't really if you do it carefully you can end up with it. So it's not something that is really straightforward. There is some fine tuning that we so, but in principle, what we need to do is we can define the border, the lower and upper border, to give you the region of X that you want to reproduce using pipeline parameters without including the other. So, my answer to your question is basically the guideline of using only 90. No. But there is, of course, different person have different personal judgment. It makes the choice become different. But to get good, to apply a good choice, there is some tips, right? Which, if we follow the tips, we may end up getting what we want. If we don't follow those, then our judgment may be messed up.
Okay, thank you. My experience, I calculate this GMT to a property from I'm using OpenMX and the package to with linear theory to calculate the real property. And I try to compare it with another paper. And I have a problem that there are some fractions that I see only consider the ground plate system. So I use combine it. I like to then to obtain the output of it.
The answer is sure, you can, but it doesn't mean that the food is ready. You may have to probably develop your own code. I mean, basically the knowledge that are dedicated to this talk is just guidance of doing so. So there are two possible corrections, levels of corrections that you need to get in order to make your calculation results for the optical properties become closer and closer to the correct ones. So we call it the correction maybe of the single particle level or two particle level. In the particle level, it means that we need to improve our brain structure. Or in the language of brain function, we need to improve our brain function from the bare brain function to what we call the trash brain function. So that this at least will correct our results to certain level, but it may still carry some feature that is not yet captured, which is called the two particle level correction. So if I show you the diagram, for instance, for optical response, typically we have bubble diagram. So each diagram two lines, right? Top and bottom. If they are not connecting with anything, these two lines may be used, each of these two lines may simply represent the pair green function or the non-effective function, or it may be improved by the trash green function. Okay, so we may do this, we call it single particle level correction. Okay, but with this alone, we are still not including it in the two particle level correction, because in order to perform further correction, we have to connect between these two lines. So there may be various approximation useful, like we may do because of the equations, and some other approaches that tackle the same thing. So that's of course not as simple to do, but at least you know the directions. If you want to go to improve the results, so you really need to either you stop at the single particle level correction, or you need to go beyond the second particle level correction, depending on whether your results is already good enough without having to go further, or they are still there. So usually we use a pragmatical approach that we don't need to do any complicated work if it's not needed. Okay?
Okay, we are 5 minutes past the hour, so let's thank Dr. Aziz again. So, yeah, I have an announcement. If anybody requests who lost their email card, you can ask the receptionist. Okay, now we shall have our coffee break. Please reconvene at 10:30 for our second speaker, and take this opportunity during the coffee break to talk and have discussion with the speakers. Thank you.
Yang Aziz dulu. Yang ini juga. Oh ini kok 15 bulan? Itu ada ini, aku potong. Enggak, tetap. Ini emang gini? Coba. Emang gambar BRIN-nya ini ya? Coba yang Pak Aziz tadi yang slide. Bukan. Maksudnya yang Pak Aziz kan tadi ada nomor 1, 2 sampai 10 yang ini aja kepotong. Sebenarnya Pak aja. Udah. Pagi dulu, bentar ya. Tadi kepotong. Ini yang siapa? R-nya hilang. Coba yang satu lagi. Hah? Iya. Nggak, yang tadi dulu. Nggak apa-apa. Kalau udah bener di situ. Kan itu yang paling kelihatan tadi. Maksudnya kita udah tahu kondisi awalnya. Yang ini ya. Nah ini. Apa ini ya? Potongnya kenapa ya? Ini ya, coba ya kita ulang lagi. Ini aja ya. Coba next ke yang over. Nah kan 1, 2, 3 nya kena. Aman. Udah sekarang balikin ke Gagus. Oke. Ini nggak apa-apa. Oh iya. Diarahkan ke sana gitu ya. We have Variational here. Connect it.
Disconnect to that, and then you can zoom to project.
Yeah. So it's double.
Okay, sounds good.
Yeah, we can try during lunch because your time is after lunch.
One talk before the lunch, the other talk after the lunch too. Was yeah. So but I think we can compare a little bit earlier and then have a try.
Actually 7:30.
Maybe like 20 minutes is enough for us.
Yeah.
Okay.
Yeah.
It doesn't always happen.
Good morning, guys, ladies and gentlemen. We shall begin our second session this morning. So our second speaker will be Dr. Gagus Ketut Sunnardianto. He is a senior researcher and member of the Quantum Simulation Research Group at the BRIN Research Center for Quantum Physics. He received his doctoral degree from Osaka in 2007. During his doctoral study, Dr. Gagus studied synchronous storage in graphene materials, and after that he switched his research into the field of molecular dynamic simulation related to corrosion process in steel and alloys. Recently, he has been interested in quantum computing, especially in variational quantum eigensolver algorithms or molecular structure optimization processes. Okay, time please is yours.
Assalamualaikum. Good afternoon, everyone. It's my pleasure to be here to give presentations. This is actually not about research because I'm actually Islam again. I'm quite new in quantum computers, and my research background is actually basic functional theory combined with molecular dynamics. So, but today I like to share the surface of the interactions to the functional automated solvers or VTA, and how to optimize using the VTA in certain quantum simulators, and then how to optimize circuit and also package size for simulating molecular simulations. So this is the outline for my two today. The first is I will talk about the intensive functional theory and molecular dynamic simulation for material science. So the materials that would like to study is actually become my motivation of to study and usage during research direction in the quantum computers. And then the second one is because we would like to use the quantum computers for molecular simulations, we try to use such kind of the quantum algorithm like the introduction of the quantum computing, quantum definition of automated solvers, and we try to benchmark for the calculations. For example, like how to choose the appropriate devices, because it also influences the computational times, and also how to integrate external library to accelerate the Hamiltonian constructions. And then the third one is we would like to optimize active speech. Active speech is the combination between active electron and also active orbital to reduce the computational times for small molecule. And then the third one is building adaptive switch, because as we know that actually Planck's time is very limited for the topic, so we need to have the smallest circuit that possible. So, and then the last is inclusion of the quantum natural graduate, because we need to have acceleration to optimize the parameter space in the quantum simulators. And then this is my background. I got studied bachelor degree in University of Surabaya, State University of Surabaya, and then master in 2012, Program Physics and Supercomputers, Paris. And then I moved to Oslo University for the integrated courses, master and also doctors. And after that, I got position as an associate in City University of Hong Kong. And then lectured at Sampurna University for 1 year, and then joined the Indonesian Institute of Sciences for around 3 years before. And then at the same time, I also have postdoctoral researchers experience in India for 1 year, and then physically researchers for around 1 year in University of Yoga, and currently I have postdoctoral researchers in NTU Singapore, and but my research field is also about the distribution of the recombinant molecular dynamic simulation for the material science, and this is my research field. This is actually about the hydrogen storage application, and also this is the hydrogen storage application, and this is for hydrogen and gate processes. You can see in here is we use density functional theory to calculate the potential energy surfaces of the hydrogen molecule dissociations before absorbed in the graphene surfaces. And the second one is about the hydrogen embrion. You can see that actually hydrogen interact with dislocation in the surface fields, and then in the granular condition. So this is multi-scales. So if we just stick in the density functional theory, and if we enlarge the size of the molecule, it will take computational time is experimenting in here. So in the futures, if we the computational quantum computer is a reality, we can use for many applications, not only for the small molecule, but also periodic crystal structures. Then this is actually my next new research. So today we will going to talk about the quantum computing form. This is actually of science. How the HIV protease enzyme protease will interact with some molecule inhibitor to inhibit the replica of the virus. So this is I will using vanillin to simulate of this quantity, and then so if we see about the how the quantum computer works this, I can say like this is the life cycle of the emerging technologies. So we can say that actually this comes from the innovation fighters, and because we already know the conceptual foundations about the superposition and outer entanglements, and then we have already know the development of the quantum algorithm such as source algorithm for factorizations for the large number, and also the algorithm for searching assorted in the large database. And then in the field of the infrared expectations, we can see that actually quantum hardware advances, for example, like IBM and also Google, Microsoft, DJT, have efforts to build the quantum computers. But again, there is still a lot of challenges in the field of the inflation expectations. But we have quantum supremacy goals in 2019. They say that actually at a certain task, Google can solve the problem, specific problem, just only for 200 seconds. Maybe compared with the classical computer that can solve the problem in those years. So this is just signifying that actually we will say that the quantum computer will be outperforms in terms of the computational capability than classical computers. So after that, we in the swap of the environments. So alpha, we already know the status of this peak of the infrared radiation, for example, quantum hardware advances from the IBM roadmap, and also the quantum supremacy with Google's. But we are still navigating the challenge. So, but the important point is the progress is still in India. So all the researchers and also companies still working on addressing the challenge, especially for the error correction code, and then the propose one of the hybrid algorithms such as variational algorithm, which use both classical and also quantum computer. And then we have one of the productivity in the later ones. So in here, we actually in the stage of, I think in the stage of this lot of alignment, there's some big player like IBM, and then Google, Microsoft, BJP, and so on and so forth. Still doing some research to address the challenge, also proposing some new algorithm to solve the problem because we still have many errors in the qubit unstability and qubit connectivity and also stability. So in years, I usually like at this hack cycle of the energy technology, I think we need to try to investment our time to be research in this one. So this is also one of my motivation to exit from information evaluation to get new skills in public computer. And then before going to quantum computers, we need to understand about neutron and also photon quantum computer. Firstly, as you can see here, what is the quantum computing? Actually, quantum computing is actually quantum computers that leverage the principle of the quantum physics, such as proposition and also entanglements. But you need to also understand what is the difference between physical qubit and also logical qubit. Physical qubit is actually the realization qubit that researchers fabricated in realization experiment, for example, supercomputers qubit and then ion trap qubit and so on and so forth. But logical qubit is, I think, this trend of qubit that we use for programming process. So, but in terms of the elaboration, for example, some people said actually around 1,000 logical qubits, 1,000 physical qubits to be formed or measures in one physical qubit to reduce the operations. So we can see that there is near term quantum computer and also quantum computers. You can see here that in the near term quantum computer, the number of qubits is still around 10 until thousands. And for tolerance, you have millions. And then for the error, it's actually the near term is indicated. And the fault tolerance, we need to include the error correction for the quantum computer hardware. And then near term quantum computer is used just only very large cases, for example, just variational simply, and then just this specific problem, this for the optimization of the small molecule, right? And then for the fault tolerance, the research is indicated for more complex problems. So in this situation, the near-term computer is early available and under development process, but for the computer is still not existing. So that's why here we in the era of these two devices, I think that it is still computers. And this is talking hardware. Actually, we have variable quantum computers. This would be types, would be results. The first is supercomputers, and then the second one is radios, and then the third one is modeling. But we have also another actually, for example, an NR quantum computer which will also tomorrow, and then operational quantum computer and so forth. So as you can see here, each qubit type has advantage. For example, is in this quantum computers, the benefit is actually height, its speed, and its fidelity, and then in the disadvantage development process for communicating devices. But the challenge is because the qubit is operated with very low temperatures, so qubit needs such kind of the diodes, electric generators, and then it also the challenge is to design the chip material which external to because the experiment will operate with very close ratio. It might be to be time module and then how about the trap ions? The trap ion, the benefit is to can be more stable. And let's go to the ion. Yes, the trap ion itself as a source of the qubit is very interactive with the environment so much compared with the source of the qubit. So this because the interaction is not so much, so the qubit have a longer time. So they also have extremely high creativity. But the challenge is to try to maintain how to manipulate to be these various measures. Because means that the measure is related to the system. And then probably this is from Sunnardianto society Kampung. Benefit is relative market and profitability and neutral limits because we can create the stages and also how to go. And then the challenge is the high efficiency from the technology. So we do actually understand about the most. If there's one of us, I think that the source of the is the also. So this is just an of the web and the sources. And this is someone moving from the ATM roadmap. So you can see that there is a lot of them in the Bitcoin. For example, in 2019, Bitcoin we have 37 and then 2020 we have 65 million. In 2021, they increased the Bitcoin 137 and the Australia 130. So you can see this one is divided the IBM research is to scale up and then this is the publication from the natures and it's usually published on the 4th December and IBM actually is first paper was included on the chip and they will usually have any hands that would give counts approximately 1,121 days. So this is the new sheets, the name is the number, and the highest so far in the IBM. So this is a global linear 20 computers from the for lights. So you can see all the country have invest so money to research in the development of the technology that you can see that there is contribution. But maybe we need to start as soon as possible from the research and also developing the government for the important in the future of the computer. You can see that there is Indonesia, but fortunately we are happy because there is a Southeast Asia country here, like Singapore, of course, and Thailand also Philippines. As you can see in here, it is I just make summarize from the previous pictures that actually Singapore is these markets. The quantum initiative program in 2017 is like program is the quantum technology. It is program is very behind. Thank you. And then quantum engineering program and a lot of investment case. So I think Singapore is already established and from 2017 until now, we produce many institutions and also some scholarship program like C50, and then Singapore still trying to recruit. We have this student also is a value from schools. So I think this is very good to start in the quantum technology programs. And then focus area is not only for technology but also basic issues in quantum physics requires development, training the students, quantum engineering program, and also communication and also devices. And then the second one is Thailand. Thailand is just starting, I think, in the technology development funds, and they invest around 6 million over 8 years for the research and development technology. And the last one is Philippines. Also, they have 70.3 and they're talking about technology. So this is such a big deal for us, I think, to see that history countries in East Asia really starting investing in research and also quantum technologies.
Actually, Thailand is now Thailand is better for so that is the
Thank you very much. Yes, this is the motivation for us also to save Not to say I mean that we have our expertise, but I think if we have opportunity to study with more people, it will solve our problem also in our research. And this is actually the basic one that we seek to understand what Ruby is actually basically of information. And then if you would like to summarize, these are shared on the block squares and the blocks full is equal to, for example, the text stage, and then in the source full is corresponding to one stage, and then the equators, the equation points, you can see that actually there's rotation states with the same probability. So, supercontrol optimization to it in outside as the computer is many, and then there's only it's only like it, only it, and graphic. And for computing, we have rotation gate and rotation gate, rotation gate. So it's depend on our purpose to select the object that will develop the results. This is and this is the challenge that we need to understand about the qubit itself. The first is like the qubit error. For example, if we have state 0 and then they try to change as state 1, which means that there is qubit error with it. And we have also identifications challenge, space challenge. They go ahead and say qubit exposed to the environment. Then the lifetime, you can see the graph is still let's say in 1 second, and then challenge is when we is now with. So it's very difficult to get the parameter space in the quantum sector, so they cannot find information's energy as the effects. And then into the challenge, for example, how to complicate the qubit longer response time, and then how to set chips that can accommodate more physical qubit for digital qubits and this stuff. So in our line of play, so because there is some error, also some challenges. So in this case, we are still in the early stage of the analysis that is discrete hardware. So we really know about how to realize the result of computers for general purpose. So in here, this is the concept of the general resolvers. This is such kind of the computer parts. We use what's classics computer and also computer. As for example, if we parts of the pre-trial stage, side 0, and then from side 0, they need to take the set of simulators, and then from this one circuit, there is data is parameter space that is organized in the classical computers. So they save the parameter data in the classical computer, but again, we send back to the quantum computing to calculate the acceleration value of the Hamiltonian. We just here is by mathematics, and then from this functional quantum softwares, we can calculate a small molecule, percentage of small molecule that not be able to. And if we would like to calculate the stage or sample structure, stage, we need to modify the functional quantum softwares, like the term that we call as the version that we still isolated about how to construct the beyond functional quantum software. And this is before using the functional quantum software, we need to maintain the with that can be read by this is, for example, if we already have by identical, for example, we have 0, state, and then we have one of the state here, we have one state, there is 1, and then we have right here 0, 1, 0, we have occupied state here 1, 0, 0. This is all the status of occupied, so we can use it as space. As you can see here, this is the example of the global excitations and also the excitations. For example, we can see this one. We have reference stage and usually in the quantum computers. We prepare the stage as a 111, zero, for example, and then we try to excite the one stage again, the excitation stage. So we have 100, 1110, and then the excitation stage in the right side we have 00101. So if the stage is assigned to the higher level of the energy, so it means that the output will be 0 and then the excited state will be 1. So it is like representation of the occupied state and also unoccupied state in here. So empty and occupied state are linked to the Fourier states during the absolute state. So this is we don't need to construct the Hamiltonian usually in Mainland. For example, we have this functionality in the Mainland, QML, QCAMs, molecular Hamiltonian. So we can generate molecular Hamiltonian based on atomics symbol and also coordinate that we have in the software. For example, we have symbol coordinate here hydrogen, and then we have number array. For example, this is location 0.0 and 0.6, and then 0.0 and 0.66 as the second hydrogen, and then just calling hydrogen equal to Hamiltonian equal to Hamiltonians. And then the parameters and then we try to bring to it. But if we try to bring Hamiltonian, we have several combination linear of the much Pauli representations acting on the circuit. For example, I0 is actually the cubic 0, and then Z is the matrix in Z. In the so we have also database for many moleculars and also some not only molecule but we have also some crystal structure that still are under the roads. Okay. So this is the example of the how to model the on this stage in the data. And also we have one tool like some today. And for example, if you would like to calculate the probability amplitude of this propagation set, as you can see that you just calculate the CFL and then you try to get devices. CFL devices, for example, this is I just using a it requires fully and then we just divide this with so we have if we apply and if we would like to have the probability of the crops and then once equal to 0 because it exists and then we construct the complete as the initial base trust. Then using QML, QCAM, stage, and then we put the electron here. And if you think what happens after we have state 1 that come from the resistance and then we would like to count now unique however just on the page now unique that we have for. So why we have for here? Because we only have like the molecule is good that the representation is to maintain the thing that we have. So to electron or the occupied state and then the electron occupied state. So the So this is the example of the algorithm for the energy calculation of the vehicle. And you can see it here, we just only set up the circuit, and then we apply now the excitation gate for 2 bit, and then we upload the circuit, and then we set up the gradient descent optimization in the classical computers, for example, and then we ensure data is the parameter space because 2 bit is actually division to one space, so we just extract 0.0 to the data, and then we for gradients to the groups, and then they just auto and then they calculate the angle, we can plot and try to compare the energy of the so it is matched here. And but how those variants of the devices, for example, like for small molecule, actually I just try to detach using the molecule, and you can see that in this several optimized. So one is we choose the devices. So our result is actually the months results of the base results of the including this results of the quantity. So we must run with the devices is the devices. So we can see the proof from here. So this is just construction of hydrogen molecule Hamiltonian by using different devices. The top one is equal to it. You can see that equal to Q and L, the device and equal to it. The second one is equal to it. And then you can see that in the time computation time for construction of using equal to it in 2 seconds, and then using likely to it we have 0 seconds. And then using performance devices in also but this is because of the small molecule. So in order to know which device that produce the very quick high consumption, and we need to try and get little values of the molecule. So you can see here, for example, in the top you can see that I just
around 3 minutes, and then if we use like a little bit minutes 7 seconds, and but if we do not define the active switch or active electron and active orbital, we need around more than 1 hour to construct the Hamiltonian. So that's why we have success to do benchmark in especially for the device quantum simulator to calculate the ground stage and also to construct the Hamiltonian of molecular orbitals. So how about if we try to interpret the PySCF methods, the external libraries for querying the Hamiltonian to reduce the computational times? So we can see here, we try to input, I just tried for cases B2, and then as usual, we try to import the libraries and also symbol and also coordinate, and then we try to define in the right side, we can see that the square red square, you can see method equal to PySCF, and then you can see the times for constructing Hamiltonian is 4 seconds if you compare with the one that we without PySCF method here. So by using PySCF methods, it will make faster the Hamiltonian constructions for a small molecule Hamiltonian. So and then we try also to set up the active electron and active orbital to reduce the computational times. We can see from these benchmarkings, and in the left sides we don't consider active space. We don't define the active electron and active orbital, but in the right side you can see that we include the active electron equal to 6, for example, and active orbital equal 6, and you can see the computational time is reduced to be 22 seconds compared with the one that without defining the active space, which combine the active electron and also active orbitals, which require around to manage. So we have already showed that the stage, and then what is this is, I mean, the number 5 is the inclusive of the one-to-one gradient. But before that, we need to number 4, I think. So we need to build in the adaptive circuit before completion to one-to-one gradient. As you can see that this is a circuit in the A. This is all the single and double excitation is actually applied in the all, not all bit. For example, we have quantum bit 1, 1, 0, 0, 0, 0, and then you can see in the A is also the double excitation is applied so many in the quantum circuit, and in the adaptive, which is only the B in the circuit B. You can see that only the relevant excitations, variations are the adaptive method. So this adaptive method will be completely selected to be in any language if we define the adaptive optimizers in the system. So this adaptive method is useful to reduce the number of excitations in the Variational circuit, and the total number of gates actually reduced. For example, from in here is to be only age just only for the excitation circuit by solving game. So if we apply, for example, in the liquidity high bias, so you can see that actually we may full here. Single and double two years, and then we try to apply for heat cam excitation to excite the single and double excitation relative to the higher stage, and actually if we try to do the amount of the excitation, we will have excitation from this. If we define that then okay, and we need to select
the novel and also similar excitation units, which contribute to the desired results. So in here we try to make the selections. The selection is just one gradient actually, the gradient of the total excitation into the set of parameter stage, and we will have, for example, in the circuit one, before defining the adaptive circuit, we have around 24 rights in the sides, and then there is adaptive in the sides. You can see that actually if we just use the select get that contribute to the output circuit, it is only 6 excitation bit. But for example, this one, if we try to plot to visualize the one sequence represented by sequence one. Sequence one is this one, sequence one, and then you can see that the sequence is almost little bit large with 8 qubit, almost all of this having experience of the execution. And then we just choose this one, and then we try to compare the result, and we have around results. So I just check that actually the translate energy is actually equal with the case if we don't specify if you don't specify the selected bit. So it's means that by using the adaptive circuit, we will have the same results without defining the selected bit result. So it's means that by using the adaptive circuit, we can reduce the rotational times. Then it is only considering reducing the rotation if applied for a certain rate. So this is the equation of the quantum number of the method. As you can see here, this is I just try to make benchmarking calculation of the related energy for some protease enzyme in HIV collagen. And you can see that actually there is protease enzyme which have a role to become the enzyme itself. So in here we try to make some individual molecule to attach to this molecule. So in order to inhibit the regulation of it. So in here the antigen of your molecule to inhibit the regulation of the virus. But for the case of this protease molecule, we try to make the extreme simplified model. You can see here, I try to define the molecule geometry from the left and then to the coordinate. We have this molecule H2O and H2, we call as overlap. And then we try to define the symbol of coordinate. This is identical out. The same with symbol and also coordinate, the same with the previous one. The one that probably the company, especially for the artificial intelligence, and just pick up the coordinate same with the missing, and then we just try to develop the Hamiltonian. And as you can see, if we try to use all the electron, this means that we will use 30 electron, and if we just using the other electron, we have to do in the equality and then it's large and it's very difficult to collect devices. So in this case, I try to define this is the active electron that we have defined before, which can be used to gravitational lines. So in here, the define is just using 6 and then active orbital 4 to 6. Instead of using 60 or 24 qubit. So after that, we try to print the total number of the qubits on the wireless because we define only the orbital is equal to 6. So it means that the total of the qubit is equal to 12. So if we try to print the total number of the excitation that starts the sub-occupied stage to the unoccupied stage. So we will have around the number of excitation by some of the excitations in the dynamics are these. But this is maybe because again we just only have the qubit stability and also qubit flat that is around less than 1 second. So we need to reduce the total of excitation again. That makes the longer the compensation. So here we have 117 total number of excitations, but we need to reduce just by using coil qubit. We make a single excitation pole and also the excitation pole. So you can see here, just only using this very source state, and then we can try to reduce the expectation value of the Hamiltonian to the ground state energy of that molecule. We have to actually the result is also about the ice molecule that brings directly. So here is the result is from years from the simulator and also from the web. So this is just IS is equal to simulator just only usable qubit instead of the system. So optimization process for problem circuit can be reduced by combining the active stage by combining the active combining the but this need experience to choose the number of the total electron also the orbital building the power of the specific model. And then this is I also just curious and then I just try to make much more just and try to cover the seeds and then we try to do the marking against because images using all electrons it require 22 and if we just using one cycle it means 30. It's required at least images include the valence electrons. It means that we need to be with this not possible for this area, I think. But this is hard to precise and give the variational spirits. And this is just only one small part, so one small part is we just need to do this less than 12 qubits. So by defining the active stage to perform one simulation related to qubits, we would like to try to optimize the role of the active electron outside the equation. And the result is like this. This is simple from simple state. We just based on our practice very much that we need to include the external libraries like PyFTF and then we define electron for this and then 6 and then we try to like include it, we try to include it and then we use the optimizers to reduce the total excitation between the and then we try to bring the circuit results. And we can see that this is the result for this thing. Well, we get different electron density. This is for the case of energy with the same qubit, qubit that we use different electron, for example, from the electron, and then 4 electrons, electron, 8 electron, and then electrons. As you can see from this result, this means that we need to design also the more active electron to be able to get the current acceleration here. We can only set up very low active electron, we have very higher energy. But if we set up more active electron, also we have collecting line for after the electron before and after the electron. So it means that this does not mean update electrons to be maximized. It means that we need to understand the behavior of the molecule itself and try to combine application of the electron instead of gates. So this is the quantum circuit behavior excitations using quantum theory. We have electron circulancy here. The circuit is very complicated. And then we also calculate with the different qubit. So if I use one, we calculate with the different qubit, but with different electrons. Like in this case, I just try to increase the number of qubit, but with the same of the number of active electrons. So you can see here qubit 8, and then I try to increase 10, 12, 14. You can see that the 14, of course, the 14 will get the most negative value of the best qubit that is. But this is 14 positive independence, we know the powers in the model. So I just try to create for this one. So my idea is again more than qubit for the system. We will get one of the engines. So this is the final problem circuit that I try to capture from the GNL circuit trading line. And the last one is the solution of the fundamental gradients, and this is just only for accelerating the function of the developer. As we know that actually in the function we need to define the Hamiltonian positions in here. So if we try to use number it means that the multiple element in the Hamiltonian process goes exponentially. So it means that this will be long. The line is less than 1 second. So we need to improve the function of the solver that can make optimization is not faster by using the number changes. So here you can see that this is the equation of this lines, and then this is the method of the and we just apply transformation from the equation space to the distribution space. And then fortunately, we have automated process of performing one number of gradient datasets. They just consist up to GNP optimizers, and the result is you can see for the molecule with the quantum number of gradient as cluster residues that produce the quantum and reductions of the elections they are with 86.9%. So this is the conclusion of the calculation. We have optimized the diagonal fundamentals of personal analysis of reality. The first one optimized, the second is in the external base, number 3 is this base, active without the fourth is other principle in this development, and then the last one is intuition. So that's all my presentation today, and thank you so much for your attention.
Okay, any questions from the audience?
Before the opportunity, I would like to ask about the GE is it possible to modify something to create a package from payment? Yes. Masih he is my assistant actually, and he is expert in collaboration. Yes, actually, if we just define directly the gate, for example, like this double excitation gate for the case of the chemistry, you can actually use also, for example, voltage to make superposition. Like for this quantum electronic quantum chemistry model is just simply just using like general rule of thumb by just using the excitation gate, and then set up automatically circuit. But if you wish like to define by yourself, the gate is okay also. So it's just only changing the execution to be, for example, OVX or OVC or OVC.
Thank you, Dr. Gagus, for the presentation. I have a question about how is the procedure to fuse the active electron and orbitals within atom of given molecule that you have shown in the presentation. Thank you very much.
Yes, this is a good question. I still do in March actually for the case of the molecules, not only this benzene, yeah, I need to have larger molecule also to know the how to set up the active site. Actually, the active site is a little bit, I think it's a little bit complicated to optimize the number of the electron to get also active electron. So at this moment, because my device only for benzene, so and you can see that if in the benzene gases, you can see if we increase the active electron equal to 10, it means that the transfer energy is a little bit higher. So it means that if we just increase the active electron, it not guarantee that the cell will be fully in the ground stage. So it means that there is good combination between active electron and also active. But the general rule of or general rule of thumb, I cannot say perfectly how to make the optimized active space because it depends also the characteristics of the electronic structure of the subprime molecule. So maybe after we have some database for some molecule, more than 20 molecule, and then we analyze, oh, this one is active space, this combination between active element and active plus. But by using this a little bit data, I cannot say perfectly how to choose the good number of electron outside the orbit for reducing because the electronic subject also.
Thank you, Dr. Gagus. So right now we are on the trial and error, right?
Yes.
Thank you.
In this calculation, could you do structure optimization or if you cannot, and then how can you have the relapse count?
Yes. In calculator, we don't set up the calculation, but we can take the relapse one. For example, if you have next distribution data, or if you have from the database, you just put the relaxation and then put in the game. So in principle, in the computer, we don't have any relaxation tools for calculation.
Up to now, you don't have and you show us the molecule system, isolated molecule system. How do you think about the boundary condition system?
Oh yes, this is for if we try to consider the boundary condition and we try to consider boundary conditions, it means that we need the number of rights. So it challenge associated with the number of qubits. So that's why in this case, the first cycle is just using isolated molecule firstly, and we find the answer appropriate for the case of the molecule, which don't any thermal correlation electron effect in this one. Because if we have boundary condition or we try to consider whether it's not any result of correlation effect in this one, I think we find different answers also. So I mean that this is the open research and part of challenging to modify functional against solvers. For example, like there is part of the functional against solvers for predicting the execution stage. For example, like variational computation that we need to study more. Really that Alternative is still we consider a new configuration also evaluates structures. So just small molecules.
So up to now, MLM is for just for the isolated molecules.
The basic principle, yes, but some people, remember they can qualify also before. But this is not the idea is really
Because if we see that the number of atoms will be related to the number of the qubits. So if we can apply the parametric boundary condition, let's say graphene again, we only consider two atoms. But benzene, we have like a couple of atoms.
good questions, but yes, maybe we need to study more about the effect of the inventory for external analysis.
Yes, I have three questions. First, we're not really reading the details of the report, but the same approach. If we have, let's say, if you want to define the design of fluid states, like in terms of the number of elements of our state, right? Since the number of basis states that can be generated by activity, whereas supposing that according to whatever configuration that we have, the symmetry and everything, we have to come up with certain further state size. It's not exactly the same thing that the power n, right? Let's say naturally we may want to require the number of qubits more than then what we actually do is then you like, for instance, expand the real space size, and the size, the number of ways that you do this, but expand the operation between some of the space, kind of spectator, they are idle,
In straightforward question is bias mentioned about the quantum stage.
To my understanding, as we do variational method, that means we have to start with certain constant state, right? So in that quantum state, of course, it has been defined the size of the qubit space. Like the length of the vector, the length of the column vector, right? And the number of elements, as in understanding, ideally it is the same as the number of states that can be verified. And two, right? What if they happen to be different?
Probably if we just reduce the number of the element stage, they set up the active orbital. So bias say that there is some niche. It's related with selected quantum circuit that produce not significant affected the results. That if we increase, for example, if we increase the number of qubits, of course the orbital should be long. But we reduce the number of orbital in the human space, yes. So in this, the adaptive optimizers think that this stage, the methane state is not contribute so much to the loss of energy. So the variance energy is equal to zero. So we neglect this information. That again mathematically is automatically when is trying itself. So if we don't adaptive optimizer, I think it's difficult to decide it. Can I have one more?
I'm just curious about whether rainy lane has been designed to be smart enough to do the radiation of the
Fundamentals.
to change from one data to another. Or we have to make our own criteria the way that so the length the question is whether you need to do a lot of putting your own criteria or failing and that's its own way of doing.
This Mainland has its own way. People as the financial tools, they choose based on the moving all the inside the but again inside I think you understand how it just because space is very important to space. Every that's and you say small parameters. So it can have to have about this equal to number of people and then it's still gets stuck in the local calculation of the current strategy, but they don't have quantum signaling inside the parameters as well, which we need to explore more.
Okay, let's end the speaker again. Now we have a group picture. I after this, for group picture. We will have a group picture, but we will take the picture not in this room, but outside the room, in front of this building. So we will have green logo over there. This is for accessibility also documentation. So please go out this building and you can walk about 1 minute, 1 hour, 2 minutes. So our team also will like you to do that. Thank you. And after the group picture, we shall have our lunch break and we shall be concluded at 1 o'clock sharp. We do for session now. Thank you.
Baru datang sinkronisir.
Tiga ini kok 1 mingguan?
Siap.
Gimana jadian, Mak? Kalau yang ininya lasernya itu bisa
Untuk teman-teman nunggu dulu ya, ini makan siangnya karena belum nyampe sekitar jam 12.30. Kalau mau keluar dulu atau kegiatan lain, nanti makannya di luar. So we are very sorry that the lunch will come slightly late because they seem to be trapped in the traffic jam and also went to the wrong location. So we are expecting them to arrive around 12:30. So we can have the lecture about that. Thank you very much.
Bapak Ibu dan teman-teman, fotonya sudah ada di website, jadi silakan di